Okay, so we were just looking at finite geometric series in the previous video, so if you haven't watched that one, I would go watch that one first. And now we're going to look at what we consider an infinite geometric series, or kind of a sum to infinity. So a little bit of a look or recap there on geometric sequence and geometric series. So these are the two formulae, I suppose, that we have been working with. Tn obviously is our sequence, Sn then has been our series, and A being our first term, or being our common ratio. And the common ratio is always just the difference, or the kind of ratio between one term and the previous consecutive term in the sequence there. So if I have a sequence like 2, 4, 8, then 4 over 2 gives me a common ratio of 2, and 8 over 4 confirms that common ratio of 2 as well. So we should have a common ratio, a constant ratio, constantly moving forward there. And obviously the ratio plays quite a big part in the sequence, and particularly when we look at the series there. And if that ratio is greater than 1, if the absolute value is greater than 1, so that's to say, I suppose, that it's a fraction, it could be a fraction, but so long as it is greater than 1, a bigger value than 1, then the values of my term Tn and Sn are going to increase as n increases. Okay, so as I get into bigger and bigger terms, if I was doing a summation, okay, think about what would happen if the ratio is bigger than 1. So say 2, for example, we're going 2, 4, 8, 16, 32, and you can see it's just getting bigger and bigger and bigger as n gets bigger. So in that case, the terms themselves are getting bigger, the summation would get bigger, and what we would say is that that sequence diverges. Okay, and this is bringing us back to kind of the limits that we talked about in the earlier video also. So in that case, that would be a divergent series because it would have no limit. Because the ratio is greater than 1, the sequence will just continue getting bigger and bigger and bigger. If that ratio is 1 exactly, then our sum is going to be like an arithmetic sequence. Because if you think about what that would mean, if the ratio is 1, if my first term is, say, 3, for example, and the ratio is 1, the next term is 3, and the next term is 3, and the next term is 3, and all the terms are just 3. And if I add those together, it's going to be like an arithmetic sequence nearly, okay, with a common difference of 3. The main one we're going to be looking at really is this last case. If my common ratio, or the modulus of my common ratio, is less than 1, and if we want to expand upon that a little bit, what that really means is if it's between plus and minus 1, then we will say that the sum has a limiting value. And all that we mean by that is if the ratio there is a fraction and less than 1, so I suppose nearly a proper fraction, okay, where the denominator is bigger than where the numerator is bigger, the denominator is bigger than the numerator. So say one's like a half, a quarter, a sixth, so on and so forth, then my sequence is going to converge to a limit. And you can kind of think about what this means. If I start with a value of, say, 2, and say I have a common ratio of a half, then I'm multiplying each of my terms by a half to find the next term. So I get 1, my next term after that would be a half itself, then a quarter, then an eighth, then a 16th, and you can see how my fractions there are getting smaller and smaller and smaller. And we've looked at these examples when we would have been introduced to limits even in calculus, that when we have fractions where the denominator is increasing and getting bigger and bigger and bigger, the fraction itself just gets smaller and smaller and smaller until it's infinitesimally, that's a very hard word to say, until it's really, 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 really small. And once it's really, 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 really small, then we say that that's nearly the limit that we're approaching. Okay, so that's kind of as small as we're getting. And a lot of the time that would be 0, I suppose, for a lot of these fractions. So that's kind of coming back to our limit rules. When we generally have a fraction, okay, with a positive power there on the bottom, then the limit for that would be 0. Okay, the limit for that would be 0. So say in this case, if n goes to kind of infinity, if n goes on forever, that's just going to get bigger and bigger and bigger and bigger and bigger until it's essentially so small that it's basically 0. Obviously it's not exactly 0, but it's approaching 0. It's getting so close to 0 that we consider that to be the limit that it's converging to. So the main ones we're going to look at are the cases where that ratio is less than 1. The absolute value is less than 1. So I shouldn't say the ratio, the absolute value is less than 1. So really when it's a fraction. Okay, this is only really going to apply when that ratio is between 1 and minus 1, or even if you want to say between 0 and 1. That's the only case that we're going to have here for these ratios. Okay, that's the only case we're going to have for these infinite series, I should say. So we can kind of look and see where that kind of comes about here to some extent as well by considering the learned proof. And I say learned proof because it should be learned. Obviously it's not learned yet, but it's one that has to be learned. So if we look at a geometric series, so let's just kind of list out what we're looking at. So my geometric series, of course, as per usual, is a plus ar squared plus ar cubed, and that would continue infinitely. Okay, if I'm looking at an infinite one, I'm not putting any end goal on that. I'm not stopping at any particular term. I'm just saying it would continue like that. If we consider kind of partial sums, and what I mean by that is kind of smaller terms or sums within my series there, we might start with S1, which would of course just be a, S2 being a plus a or, S3 being a plus a or plus a or squared. And I could continue that on until I get up to, say, for Sn, for example, which we already know to be a or to the power of n minus 1. And I could continue that on kind of indefinitely nearly. And I could continue on with Sn plus 1, Sn plus 2, and so on and so forth. If we want to get the sum to infinity, so for the sum to infinity, and this is, I suppose, written out in even more kind of minute detail really in the notes here, but for the sum to infinity, we can take the limit of these. So we're going to consider each of these partial sums really arises from my Sn formula, so I'm going to take the limit of that formula. So if I take the limit of Sn as n goes to infinity, so I've been looking at S1, S2, S3 all the way up to Sn. I want to see now, if I just kept going and looked at all of those, where would I get to? What would the end result be? So we're really looking at taking the limit as n goes to infinity of a 1 minus or to the power of n over 1 minus or. Okay, so that's kind of really where we're getting to here to some extent. So let's kind of see what we can do here. Can we do some sort of manipulation? We really want to isolate the part that has n here, because anything outside of that is not going to be impacted by our limit. So in order to do that, we're just going to make a little subtle shift here and kind of shift this top multiplication just off the fraction, still the same meaning, but we're just kind of taking it off the fraction so that we can then make another subtle move to bring that entirely outside of the limit. Because the part that I have on the left hand side here, the a over 1 minus or, there is no n part to that, so it's not going to be impacted by our limit at all. The part I have on the right hand side is going to be impacted by the limit because of the n value up the top here. So if we want to consider kind of what's going to happen in this case, we need to think about the values of or. Okay, we need to think about what this is going to apply to. So for an infinite series, it only converges, or a series only converges, or I suppose, so the limit only converges if or is between minus 1 and 1, or even as we said there, the absolute value is less than 1. So that's what we're looking at in the first place here. So we will only get this limit, it will only exist or be possible if that value for or is between minus 1 and 1 or less than 1. And essentially what that means is if it's a fraction, okay, if it's some sort of proper fraction. And what's going to happen to a fraction like that as n gets bigger, if we think about what would happen to or there, as n approaches infinity, or to the power of n is going to approach 0. Okay, and where that kind of comes from is we're thinking of or as being some sort of fraction, so you can think about it as being 1 over n even, for example, or 1 over p for some p, all to the power of n. And as n gets bigger and bigger and bigger, that fraction is being multiplied by itself more and more and more and more and more until we reach a point where it's so small that it's nearly it's getting so close to 0. So we can consider that limit. And again, that's all coming back to really our limit rules here, kind of restating what's said in that video and what's said in our kind of calculus one as well. But using that fact then, in order to compute this limit then, we can say that a over 1 minus or times the limit as n goes to infinity of 1 minus or to the power of n is the same as having a over 1 minus or times 1 minus 0. So computing my limit there, which is a over 1 minus or times 1, which of course is just a over 1 minus or. And that last part there is really the key part here. Okay, and that formula that we have at the end, a over 1 minus or, is what we call our sum of an infinite geometric series, okay, or the sum to infinity of a geometric series. And it only applies, as we've said there, where the common ratio is between 1 and minus 1. So we're thinking of kind of proper fractions here. And we have kind of explained why that is for ourselves as well. So because we're looking at a proper fraction where the denominator is going to be bigger, then as the fraction itself is multiplied by itself over and over again, the overall fraction is going to have a smaller value. Okay, and this is all coming back to kind of our understanding of limits to some extent as well here. But the main thing to know really is to be able to kind of reproduce that proof to some extent, particularly this second half here as well. So particularly this second half, some of the proofs you might see as well kind of start nearly at this point. I think it's always good to show an understanding of that kind of partial sum, or why we kind of go for that limit of Sn, because we're looking at those individual sums as we work through, but particularly for this second half here. And as I say, it's done out in perhaps a little more clear detail in the notes, obviously, than is done here, but it's more to get that understanding here, and then the notes will kind of give you somewhere to actually just kind of learn it off from to some extent. But the main kind of thing coming in there is that idea of or and how that impacts the limit there, and kind of calculating or computing that limit. So applying this then actually ends up being fairly straightforward, I suppose, to some extent. Okay, and let me see, I think I have covered up the actual question here as well. I have. So applying it is quite straightforward really. So looking at the information that we have here for this first one, a is 1, my common ratio is a half divided by 1, which of course is just a half. The sum to infinity, as we've just worked out, is a over 1 minus or, so it is 1 over 1 minus a half, which is 1 over a half, which of course is 2. So if I was to add that sequence up to infinity as far as I possibly could, I would approach a value of 2. That's kind of what the sum to infinity would be. That's the limit that I'm converging to for that series. Similarly over here, if I kind of try the same idea again, if a is 5 and my common ratio is 5 minus 5 over 3 divided by 5, I get a ratio of minus 3, or negative a third. My a is 5, my ratio is minus a third, so 5, 1 plus a third, which is 5 over 4, 4 over 3, which is 15 over 4, okay, as my sum to infinity. Looking then at some summation notation, as we did with the initial or finite series, first thing we want to do really is kind of work out, or so show that it converges, and then kind of look at the different sequences that we have here, kind of listing out some values maybe. So that's kind of what we're going to start with, is kind of see what the values are. We know it only converges. Okay, remember, converges is kind of where it converges to some sort of limit. It would eventually approach some sort of limit. Only does that if the ratio between the terms is less than 1, or the absolute value of the ratio between the terms is less than 1, or that the ratio is between minus 1 and plus 1, some sort of proper fraction. So we can kind of have a look at what the terms are here. So the initial term would be when n equals 0, and that's just going to be 1. My next term is when n equals 1, and that's just 3x squared over 4x squared plus 1. My next term then is 3x squared over 4x squared plus 1 all squared, and so on and so forth. So I end up here with a being a value of 1 and or being a value of 3x squared over 4x squared plus 1. That's by dividing my second term there by 1. Okay, I want to show now that that is going to be less than 1, or the absolute value of that is going to be less than 1. And to do that, we can kind of consider the fraction itself here. What we want is, we want a proper fraction. So we want 4x squared plus 1 to be greater than 3x squared. We want 4x squared plus 1 to be greater than 3x squared. And if we even, you can consider this if you want to as a kind of, nearly as a little sum for us to work at, or we can just kind of look at it by eye a little bit here. So long as x is greater than 0, which is what's given to us here, if x is greater than 0, then 4x squared is always going to be bigger than 3x squared. And of course then if 4x squared is already bigger than 3x squared, then 4x squared plus 1 is definitely going to be bigger than 3x squared. Okay, so in that way we've kind of already shown, or can show fairly easily, that this is going to be a proper fraction where the denominator is going to be bigger than the numerator. So what that means for us here then is that my value for or, the absolute value of it, is going to be less than 1 as required, which means it does converge. Okay, so again, some understanding of kind of what this means for fractions nearly coming in here rather than even limits. Okay, so kind of a basic understanding of our fractions here. So looking then for s to infinity, using what I have here, 1 over 1 minus 3x squared over 4x squared plus 1. And now we're really getting into a little bit of algebra here to some extent. And if we were to tidy that up here, I'm going to get 4x squared plus 1 over x squared plus 1. Bottom here. Okay, so just doing some kind of quick tidying there. 4x squared plus 1 over x squared plus 1. Okay. Looking at the second part of the question, they're asking us to evaluate the sum from n equals 0 to infinity of 12 over 17. So what we want to do is we want to see, can we take 12 over 17 and compare it to our kind of expression that we have inside the brackets here? Is there a value of x that would satisfy our expression and give me 12 over 17? Because if there is, then we can use our sum to infinity to work it out. So let's kind of have a little look here. We want 3x squared over 4x squared plus 1 to be equal to 12 over 17. If we focus even on the 3x squared, that's going to mean that x squared would be equal to 4 and x would be equal to technically plus or minus 2, but we know x is greater than 0, so that would be plus 2. We can check, does that work for 4x squared plus 1? And that's going to give us 16 plus 1, which is 17, so it does. So we do get an answer of 12 over 17 as required. So what we can do then is we can take our sum to infinity as we had it here, and we can substitute in x equals 2. And finalizing that out, 17 on the top and 5 on the bottom. Okay, so my sum to infinity of 12 over 17 is going to be 17 over pi. So getting into some exam questions now. So this exam question, I suppose, is a practice across the geometric sequences and series, really. So it's a practice kind of across all of them, making use of everything that we've kind of had so far. So everything that we've kind of come across here. So Alex gets injections of a medicinal drug. Each injection has 15 milligrams of the drug. Each day the amount of drug left in Alex's body from an injection decreases by 40%. So the amount of the drug left in his body after t days after a single injection is given by 15 times 0.6 to the power of t, where t is an element of 4. Find the amount of drug left in Alex's body 2.5 days after a single 15 milligram injection. So 2.5 days after the injection means t is 2.5, so 15 times 0.6 to the power of 2.5, and working that out for ourselves here is going to give me an answer of 4.1828, and we're asked to 2 decimal places, so that's approximately 4.18 milligrams of the drug left. So 4.18 milligrams of the drug left in its body after 2.5 days. How long after a single 15 milligram injection will there be exactly 1 milligram left? So in this case, we want to find t when what we have, I suppose the formula that we have here, and were we given any name for this formula, we can call it maybe A here for Alex. We want to find t when the amount of the drug left is 1. So we're essentially saying that the 15 times 0.6 to the power of t here needs to be equal to 1. So we get 0.6 to the power of t is equal to 1 over 15. We've kind of two ways of approaching this one. We could do log to the base 0.6 of 1 over 15 is equal to t. Using that then to work out a value for t is going to give me, so answer here, an answer of 5.3, and we were asked to one decimal place, so 5.3 days. We could also here have taken log of both sides, or ln of both sides. So t ln of 0.6 equals ln of 1 over 15, and t is ln of 1 over 15 over ln of 0.6, and we'll just double check that that gives me the same answer, which it of course should, but should being the operative word, and we do get the same answer of 5.3 days. So either way, 5.3 days appears to be the length of time there. So Alex is given a 15 milligram injection of the drug at the same time every day for a long period of time. Explain why the total amount of the drug in milligram in Alex's body immediately after the fourth injection is given by 15 plus 15 times 0.6 plus 15 times 0.6 to the power of 2 plus 15 times 0.6 to the power of 3. So let's kind of look at how many injections he's gotten. He's gotten 4 injections at the same time every day. Okay, so each injection he got kind of, I suppose, at the same time every day across 4 days. They want to know how much is in his body at the time he gets the 4th injection. Okay, by the time he gets the 4th injection. So at this initial time, I suppose, this 4th injection that he got is today. Okay, so that's today. So that has a time of 0. So we can look at kind of how much of that is left in his body. It's still 15 milligrams. He has injected 15 milligrams. It's still that day. He still has 15 milligrams left. The 3rd injection he got, for that one, t is 1. Okay, it's been 1 day. So that's 15 times 0.6 to the power of 1. For the 2nd injection, hopefully we're kind of catching on to the pattern here. T is 2, so that's 15 times 0.6 to the power of 2. And for the 1st injection that he got, T is 3. We have 15 times 0.6 to the power of 3. So overall in his body, he now has each of those. Okay, he has all of that kind of amount of the drug in his system, which leads me to a sort of series here where I'm adding those different values up. And that's kind of why he has that cumulative amount of the drug in his system. But some sort of formulaic layout like that just allows you to really show off why you know that, and some sort of then note at the end to kind of really explain it as well as to why that's the amount in his system after that amount of time. Find the total amount of the drug in Alex's body immediately after the 10th injection. Give your answer in milligrams correct to 2 decimal places. So let's kind of have a look at what we have from the previous one. So we kind of know now that overall this is kind of the pattern or sequence or series that his injections or the amount of drug in his body is following. And in this case, A is 15. Okay, so A is going to be 15. The common ratio here is 0.6. It's going up in 0.6 here, and we want to know how much he's going to have after the 10th injection. Okay, how much he's going to have after the 10th injection. So this is the 1st injection, 2nd injection, 3rd injection, and so on and so forth. So we're going to find Sn using our formula from before. We're just looking at the finite sum first of all here. So 15 times 1 minus 0.6 to the power of n all over 1 minus 0.6. To find S of 10 then, I just need to fill in 10 for my value of n then. Okay, and I can use my calculator then to help me work that out. There, 0.4, and that's going to give me an answer of 37 37.2733, which to 2 decimal places is 37.273 milligrams of the drug. So after 10 injections, he should have approximately 37.27 milligrams, because you're bearing in mind that the drug is kind of wearing away after a certain length of time as well. He's kind of has very little left from the very first injection there by the time we reach the 10th injection. So we're asked then to use the formula for the sum to infinity of a geometric series to estimate the amount of drug in Alex's body after a long period of time during which he gets daily injections. So following the same sequence, we have A is 15, my ratio is still 0.6. We're content that because the ratio is 0.6, that has an absolute value that's less than 1, so it will converge, so it will have a limit as we take the sum to infinity. So my sum to infinity is A over 1 minus OR, which is 15 over 1 minus 0.6, so 15 over 0.4, and that's going to give me an answer of 37.5. Okay, so if we kind of keep, after a long period of time, there's going to be approximately 37.5 milligrams of the drug left in Alex's body there. Okay. Moving on from Alex a little bit, we're going to look at Jessica now. So Jessica also gets these daily injections of a medicinal drug at the same time every day. She gets D milligrams of the drug in each injection, where D is an element of OR. Each day the amount of drug left in her body from an injection decreases by 15%. Use the sum of geometric series to show that the total amount of drug in Jessica's body immediately after the nth injection, where N is an element of OR, is 20D times 1 minus 0.5 to the power of N all over 3. So we need to kind of break this down, and we can use some comparison to Alex's situation here. So in Alex's case, the amount of the drug left in his body decreases by 40%. So what that means is there was 60% of it left in his body, and that's where we got the 0.6 from. So based on however he started with, because it decreased by 40%, there was 60% of it left. Because this decreases by 15%, that means there's 85% left in her body. Okay, there's 85% left in her body, or 0.85. So what I'm considering there is that the ratio this time is 0.85. We're kind of decreasing the amount of drug left in her body by 0.85. We don't know how much was initially injected. We're just told that she was injected with D milligrams. So at the start, in the first day, her first injection would have injected her 15 milligrams, and that's what she would have had in her system for that first day. So to find my overall sum here for n days, I'm going to use my sum, or my finite geometric sum, or series. Filling in those values, 0.85 times 1, or sorry, excuse me, that's not, D is A, 1 minus 0.85 to the power of N, all over 1 minus 0.85. Okay, and then it's really just a bit of manipulation for us here to some extent. So D times 1 minus 0.85 to the power of N. Okay, the top part's looking fairly similar. 1 minus 0.85 is going to be 0.15. We need to maybe consider what that's going to be. So 0.15, or even 1 over 0.15 is the same as 20 over 3. So 0.85 is the same as 0.15 is the same as 3 over 20. So looking at how that relates here. Three over 20, and then based on our fractions, kind of from what we've done before, that's 20 times 1 minus 0.85 to the power of n. Okay, and all over 3, and that matches up with what we wanted there. Okay, so you can see there how useful it was for us as well to go back and compare to Alex's situation, and that kind of helped us along with starting off the question. So immediately after the 7th injection, there are 50 milligrams of drug in Jessica's body. Find the amount of drug in one of Jessica's daily injections. Give your answer correct to the nearest milligram. So after the 7th injection, so that's S7, she has 50 milligrams. So after 7 injections, she has a total of 50 milligrams. So making sure we know here that that is a total, I suppose, in this case. We're using our formula that we had previously there. So that was that Sn is 20 times 1 minus 0.85 to the power of n all over 3. This time we need to sub in 7. 1 minus 0.85 to the power of 7 all over 3. And that should be equal to 50. Okay, and again at this point, it really does come down to a bit of manipulation for us here then. Okay, a bit of kind of algebraic manipulation. No, sorry, I'm missing D there. I knew I was missing something, the one thing I have to actually work out. So let's see, that's 150 then multiplying by 3 there. So I have D is 1 minus 0.85 to the power of 7 equals 150 over 20, which is of course 15 over 2. And we can then divide that by this expression inside my brackets here. And we can just double check to see that we've got that kind of correct here. So divided by 1 minus 0.85 to the power of 7. Okay, and I get an answer of 11.0388, and I'm asked to the nearest milligram. So to the nearest milligram, that would be 11 milligrams. So each day, Jessica's been getting injections of 11 milligrams. So the key thing there really is us recognizing that 50 milligrams would be the result of a series of kind of daily injections and that kind of summation of those. But really, again, relating it back to Alex's example there really does help us or give us kind of an edge then on answering that question. Looking at another question then, okay, we're going to look at Mary. So Mary's throwing a ball here. So Mary's throwing a ball, and this again, fairly common, kind of nearly a book style one here as well. Mary's throwing a ball onto level ground from a height of 2 meters, and each time the ball hit the ground, it bounced back up to 3/4 of the height of the previous bounce. Okay, complete the table to show the maximum height in fraction form reached by the ball on the first 4 bounces. So on the kind of initial zeroth bounce, if you like, it has a height of 2. The next time that it, or kind of after the first bounce, we want to see where it's landed. It's reduced by 3/4 of its height, so it comes to 3/2 then. If we multiply that by 3/4, then to get kind of our next height here, let me see, what am I doing here? 3/4, yeah. If we multiply that by 3/4, that's going to give me 9/8. Multiplying that by 3/4 is going to give me an answer of 27/32. And multiplying that by 3/4 is going to give me an answer of 81/128. Okay, just multiply by 3/4 each time. Find in meters the total vertical distance up and down that the ball had travelled when it hit the ground for the 5th time. Okay, so find in meters the total vertical distance up and down the ball had travelled when it hit the ground for the 5th time. So if we kind of think about what happened here, the ball starts up here, travels down a distance of 2. It then travels up a distance of 3/2 and back down that distance of 3/2. It then travels up a distance of 9/8 and back down that distance of 9/8, up 27/32, down 27/32, and then lastly kind of following the same idea here, up and down again. So the initial distance is the only one that's kind of on its own here, and then each of the rest of the distances comes up twice, because we're going up and down. Okay, and we can kind of compute that for ourselves here. So 2 plus, let's do that sum on the inside here. So 3/2, 9/8, 27/32, 81/128 gives me 525 over 128, and working all that out, it gives you 653 over 64 meters. Okay, giving our answer in fraction form, so we have our answer in fraction form there, 653 over 64. Okay, and we could convert it to a mixed fraction if we really wanted to, but that's absolutely perfect. Okay, so just making sure there, I suppose, the difference that we have to multiply each of those kind of second results by 2, because after that initial one, it's going to bounce up and down from that same height. So when it reaches that height, it kind of reduces itself back down. If the ball were to continue to bounce indefinitely, find in meters the total vertical distance that it would travel. So we can kind of compare our sum here. We have 2 plus 2 times 3/2 plus, what was our next one? 9/8 plus, and we're essentially saying what would happen if that continued on. And what we have in here is a sequence. Okay, what we have in here is a sequence. It's an infinite sequence. Okay, it's an infinite. If we're going to bounce indefinitely, that's going to go on infinitely. So we need to look at what the first term of that sequence would be. It would be 3/2. And my ratio is going to be the reduction that I have, which is the 3 over 4. That was the reduction in the height that we had there. So to find the sum to infinity of that part, that's using our same formula as before, a over 1 minus or, so 3 over 2, 1 minus 3 over 4. And if I work that out for myself here, so 3 over 2, 1 minus 3 over 4 gives me an answer of 6. Now that is just the answer for this sum inside here, this infinite sum inside here. So to work out my overall answer, I need to do 2 plus 2 times 6, which of course is 2 times 12, which is 14 meters. So if the ball bounces indefinitely, it should reach a total kind of travel distance of about 14 meters. That's what the distance should kind of approach to or approximate to. So kind of the key there, really identifying that the summation we're looking at isn't actually the full question here. It's actually only part of the question, and it's the part inside the brackets there, and then being able to relate that back to the rest of the question. Okay. The last little type that I want to look at here is a recurring decimal, and this is just something we can kind of look at fairly quickly, but a recurring decimal can actually be expressed as a sum to infinity of a geometric sequence. And what this means is we can prove then that a recurring decimal is a rational number. Okay, is a rational number. It's obviously ratio there, absolute value of the ratio. The symbol we use, you can kind of see it here, it's a little dot, and you usually see it above a number. So we might have a little dot above a number, and that represents that it's a recurring number. So if we have 3 like that, it just means that the decimal has 0.3s that continue infinitely. What I've said as well is if we have more than one number, so maybe we have 2, 0, 6, 7, what that generally means is that that string of numbers is repeated. Okay, and that's kind of what we're coming up with there in terms of that, in terms of our recurring decimals there. So something to, I suppose, just recognize, making sure that you're kind of familiar with that notation for a recurring decimal. It's on your calculator, and you should be able to kind of see it for yourself. You probably have seen it in questions. Looking again, I have covered up my question again. So let's express each of these decimals as a sum to infinity and use that in order to express it in fraction forms, because as we saw, those sum to infinities, they tend to reduce to a nice fraction because the formula itself is in fraction form. So what we want to do is we want to look at this as a sum to infinity of 7 plus 0.3 plus 0.03 plus 0.003 plus, and what we're really doing here is this 3 part here is obviously 0.3, and then I'm considering this to be 0.03, and I'm considering this to be 0.003. We're really taking advantage of place value here, which you would have done in senior infants, I don't know, first class, I'm not sure, primary school. So we're really looking at place value here, making sure we kind of remember that idea. So what we're looking at, kind of similar to what we had already, the expression in brackets there is a geometric sequence or a geometric series, where the initial term is 0.3 and the ratio that we have is 0.03 divided by 0.3. We can double check what that gives me. It gives me 0.1. That's my ratio. The ratio does satisfy what I wanted, which is that it's a proper fraction. It's less than 1. So we can use my sum to infinity there because we're content that it is going to converge. So 0.3 over 1 minus 0.1, which is 0.3 over 0.9, which is going to be 3 over 9. So adding that on then to 7 plus 3 over 9, and that's going to be 24 over 9. No, excuse me. What am I doing? 3 over 9. Let's reduce that down first. 1 over 3. See, this is what I get for thinking I could remember the answer. 1 over 3, which would be 22 over 3. Okay, and if we're unsure, or if we're doing these sort of questions, the best thing we could do would be to check our answer. So we type in our 7 point, and I want to get my recurring decimal symbol here. So let me just see, can I find it on this calculator? Hopefully we can. 7.3, or alternatively we'll go the other way around and we'll type in the fraction and see, does it give us the same result there for my fraction? I don't seem to be able to get my recurring decimal here, which is a bit annoying. No, okay, so let's try and go the other way maybe. But on your own calculator, the best thing to do would be to try and type that in using your recurring decimal symbol and show that that's the fraction that you get. Going the opposite way for ourselves here, I've typed in the fraction and we can see that we do end up with the decimal that we started with. Sorry, I'm still trying to look there to see could I find it. No, that's not it. Okay, anyway, let's look at the second one here. So 2.463, which means 2.463.463.463. So slightly more extended here. So same kind of starting point. So 2 plus 0.463. So that's going to be this part here. Okay, and we can do plus 0.000463, so ignoring the initial 463 that we had, and so on and so forth. When they get quite big like that, sometimes we just have to shut it down a bit quicker. So we're looking at same idea again, infinite series, first term 0.463, ratio 0.000463 divided by 0.463, which is 0.001, or 1 over 1,000. So my sum to infinity is 0.463 over 1 minus 0.001. Okay, which is going to give me 463 over 999, and adding that on to 2 then, it's going to give me an overall answer of 2461 over 999. That's my recurring decimal. And again, we can check that as before. If you type it into your calculator, you'll get that overall answer result here. So we have 2 questions here, 2 exam questions on that, following the exact same idea. Okay, so I'm going to leave those exam questions, I think, for you to do for yourself. There's really nothing extra in those sort of questions there. Now you can see both of them, 2003 for the first one, 2012 for the second one, so I suppose a little bit more recent, but overall maybe not something that comes up as frequently. Now there's some additional exam questions for you to practice as well. These are kind of looking across the kind of spectrum of the questions that we've done. The first one, even there, you can kind of see is bringing in a little bit of trigonometry with the length of the arc there, kind of area. I might do a video for those separately, but just ones to work on for yourselves. But mainly here, the main kind of takeaway is about that infinite series. Okay, making sure that you kind of understand that idea. When does it occur? So what needs to happen for it to converge? That idea of it being related to the ratio, and then just being able to apply it. The actual application itself is fairly easy because the formula itself is quite short. But just making sure across that with our geometric sequences and our series that we're kind of content with what they are, what each of the parts of the formula mean, and when we can use them.